Okay, let's get started. Welcome back. Any questions or comments before we start today's lecture? All right, I have a couple of announcements. One is there's a new homework posted, and it's actually kind of an extension of your last homework. You're going to just build a folded cascade OTA to meet a certain, given specs, and you have quite a bit of time to do it. You don't have to finish it in a week. I didn't want to ruin your spring break in case you have something good planned. But if you've never simulated a big circuit, I encourage you to get started early because, there's always issues to resolve. So, your common mode feedback's not working quite right, or you forgot this transistor. So get started early if you've never done a big circuit before. Otherwise, it should be a pretty straightforward problem set. It's also kind of a practice for your project, and you'll notice that the project description's also been posted, so you can get started on your project right away. The project is due, I think, on May 4th, which is one of our last lectures, and so you should have about, 5-6 weeks to work on that as well. Questions or comments? For the project, you can work individually or you can work as a team of two. And basically, if you look at the project and you look at previous year's projects, for several years, students have done a very similar design. You're designing an OTA to meet, again, a given set of specs. And the specs are, of course, tough, especially with technology scaling. And so I think what's interesting about this project is for several years the students have been doing their designs in 0.35. So you guys are going to 0.18 on a 1.8 volt supply. It's definitely going to be challenging. So my guess is that if you do a Google search and look for previous projects and you try those out, they probably won't work. There's not enough headroom. And so really the goal of the project is to get, to meet certain accuracy requirements, certain settling time requirements, and to do that with the lowest power consumption possible. And so there's lots of room for innovation. You can try to use circuit techniques that aren't very often used. You can try to come up with your own. I think you'll have fun with it. Okay. All right. So let's get back to lecture. So we've been talking about slew rate and settling time. And we briefly talked about some techniques for improving the slew rate. One technique was to basically just degenerate our input transconductance. So instead of having a very small input range, let's say like this, let's say this is only 100 millivolts or so, we could degenerate it or size the devices appropriately so that we get a larger input range. So maybe now this is a volt. And so as long as the step input is less than a volt, we don't slew. Or equivalently, the amount of time we have to slew is now reduced because if the step is above a volt, then we only have to slew during this time when the amplifier is in this region. But as soon as it gets back into this region, it goes linear again. Of course, this reduces the GM of the input stage, right? And so we're going to look at a few other ways of improving the slew rate. So let's just review that. So that was degenerate input stage. We could appropriately scale the bias current so that overall we see an improvement in the slewing. This doesn't work for BJT, but it works for MOSFETs because the square root dependence on the transconductance. And basically, there's not that much we could do. For instance, a few lectures back, I talked about we could use a PMOS input stage because a PMOS transistor already has a lower GM over I than an NMOS pair. So automatically, you get a larger input range, but also has lower 1 over F noise. So that's also a kind of an added benefit in most technologies. But then thermal noise becomes an issue because your GM is less since your input referred noise is higher. So it's definitely a trade-off. Okay. So the approach we're going to look at now is kind of other circuit techniques. And I'm going to look at an amplifier in detail to understand exactly how these techniques work. So I'm going to draw a folded cascode amplifier. And I'm going to draw a pretty complete schematic so we get the entire picture. And let's see. And just for illustration, I'm going to use a single-ended output stage. So this is our current mirror here. And let's call this VB1. This is our high swing bias voltage. Let's call this VB2. This is just some DC bias voltage. This is our PMOS current mirror. And then here is our folded cascode stage. So this is our input transconductance stage, right? This is our cascode transistor. This is a current mirror, and this is the output, which is single-ended. So this circuit automatically does a differential single-moded conversion, just as you've seen before, through this current mirror. So the current, if I were to inject a differential current like so, this current will flow through this low impedance point, of course. This current, likewise, AC current, will flow through here. This current gets mirrored, so these two currents get summed and applied at the output. Okay, let me just label a couple things. Let's call this I bias 1. Let's call this I bias 2. Transistor M1, M2, M3, M4, M5, M6, 7, M8, M9, M10. And let me just call this transistor MX. This is kind of our reference transistor. So let's write down it's a single-ended output. And what's kind of interesting about this circuit is that the biasing in this leg, right? None of these currents are actually fixed. This is a mirror. So the current that flows through transistor M5, M6 is really the difference between the current of M1 and the current of M3, or likewise the current of M2 and the current M4. So we can say that the bias voltage, drain current of 5, is equal to drain current of 3 minus drain current of 1. And the drain current of 3 is, let's say, some factor times mx. Let's say it's the current of mx. Let's just call that m times I bias 2. Let's just call this I ref. Okay. And then the drain current of 1 for 0 input is just I bias 1 over 2. And let's say that I bias 1 is also some factor times this reference current. Let's say it's n. Okay. And so, of course, over process and temperature, we want this transistor to be conducting current. So you can see here that if you were designing this folded cascode, you might, in order to minimize the power, you would observe that, first of all, you need lots of current in the first stage, right? That determines your transconductance. And also, the input referred noise is determined by the GM of these transistors. The second leg, though, is only contributing a non-dominant pole, right? It's not contributing a dominant pole. Great, we want this capacitance to be large. And it's contributing a non-dominant pole because of these transistors, and to a lesser extent because of this current mirror. So really, we could turn down the current in the second stage and not deteriorate the performance too much. But at the same time, we have to have enough current so that the non-dominant pole isn't too small, right? So that's essentially the consideration. There's also an added benefit that if you run the second stage here at low current, you get higher output impedance. So that helps with the gain as well. So how low can you make it? Well, practically, of course, ignoring the non-dominant pole consideration, you can see that it has to be over process and temperature. You have to make sure that these M and N factors don't change too much so that you don't end up getting negative current, right? Negative current means the second stage shuts off. Okay. All right, so now let's look to see what happens to the circuit when we apply a large input. And in fact, it's a little bit surprising what happens. What we'll do is we'll first assume this is an ideal current source, and then we'll actually take the realistic situation where this is actually a real current source. Okay, so I'm going to apply a large, let's say I apply a large step input. Okay. And essentially, let's say I increase the voltage in the negative direction. So M1 turns on hard, M2 turns off, and so all the current I bias 1 is flowing through M1. So let me draw that like this. And M2 is basically off. This is M1. And so really it's not doing anything. Even though it's connected here, there's no current going through it. And so all the current I drain 4 flows into M5. And down here I'll just draw this part of the circuit as a mirror, this block. So these are just tied to some bias voltages. And so we can see now that the current, all the current of I drain 4, which is just some ratio of this current, I ref, will flow into this mirror and flow over here and discharge the output. Okay? So the question is, how much current flows here? Anybody want to take a stab at that? Well, it's not rocket science, right? It's the difference between this current and this current, right? We've designed this current to be larger than I bias over 2, right? So what's going to happen here? Anybody want to guess? Yeah, potentially we could get negative current, right? If this is a real current source, let's say I've designed this circuit so that I bias is greater than I drain 3, right? Remember, I drain 3 is bigger than I bias over 2, but it might not be bigger than I bias, right? So if this condition is satisfied, that means that the current is actually going to be in the wrong direction, and it's actually going to, instead of helping you discharge, it's going to help actually charge up and fight against the output. But in reality, this is not an ideal current source. In which case, what's the likely situation? Think about this voltage. How does this voltage swing? Drain of M1. If I'm pulling more current than supplying current here. Oops. Yeah, it'll go down, right? So this voltage will actually decrease. In fact, this voltage will keep decreasing until the point that this voltage here is low enough, right? It'll decrease, it'll just keep decreasing until transistor M1 and this current source go into triode region. At which point, the current is automatically lowered so that it equals the current of M3. And so at that point, this current is equal to this current is equal to 0, and so the only discharge current is in fact I drain 4. Okay? Questions?
So why the current go to the meter has to be go down to 0? Why cannot be negative?
So this transistor is biased, right, to conduct current in this direction, right? And for this to actually go into reverse conduction, this voltage would have to go above, right, this voltage. But we're actually discharging this through here. So this voltage is actually going negative. So there's no opportunity for this transistor to flip direction and provide negative current. Okay. So now we're going to make a simple modification to the circuit and show you that this actually does help the situation out. So what we're going to do is we're going to insert two we call clamp transistors here. Okay, and let's call this M11 and M12. Okay, so how do these transistors help? Well, let's again, same argument. I apply a big step input, M2 turns off, most of the current is flowing through M1, and as this point basically drops, right, then this transistor begins to conduct, right? It starts to turn on. And so now you can see that potentially, if the voltage here gets low enough, the current supplied by this extra transistor M11 plus the current of M3 could equal I bias, at which point we reach a steady state and this voltage doesn't drop anymore, right? So first of all, this transistor can clamp this node. Where does the current of M11 come from, though? Let's connect to a gate here. Can IREF supply a current going down in this direction? Remember, IREF is fixed.
From M4?
M4? M4 is this transistor. Do you mean this transistor? No? Right, this current M4, we're talking about this node here. The current of M4 is going through here and getting mirrored to the output. All right. So where could this current come from? Well, clearly it's got to come from MX, right? You guys are just being shy. So MX is a diode-connected transistor. If this voltage changes, right, then I could actually change the current of MX. So the extra current comes from MX. So basically, transistor M11 will clamp this node. The extra current that it draws from MX will equalize the I bias current and the I drain 3 current. And additionally, because I'm drawing more current from MX, what happens to the current in M4? Right? It also goes up. So that means now I have more slewing current flowing to the output. So there's a double benefit to having transistor M11 here, in that it clamps the voltage and it supplies larger current during slewing. Okay? And of course, transistor M12 does the opposite when the input is actually a positive step rather than a negative step. Any questions about that? Okay, so let's write that down. So transistors M11 and M12 are voltage clamps to limit the change in voltage during slewing. I guess I didn't say this explicitly. So what's the big deal? So, okay, you've provided some more slewing current. That's a good thing. Why am I calling it a voltage clamp? Well, it's pretty undesirable to take transistors into triode, right? So if without the clamps, this transistor goes into triode, this transistor goes into triode, and so when the slewing is all done, this circuit has to become a linear circuit again. That means this transistor has to turn on, this transistor has to turn on. It takes time to do that. So that extra recovery time adds to your slewing time. So that if you calculate the slewing time, you find you underestimated it because you assumed that everything went back to normal instantaneously. In reality, all these extra capacitors and nodes have to charge and discharge in order for these transistors to enter let's say saturation region from linear region. So by clamping this voltage and preventing these transistors from going into triode, actually you're going to considerably increase the recovery time. So this will improve, not increase, decrease, improve recovery time. Okay, it's a lot like a Schottky diode you'd put in a TTL cell, right, to prevent that triode transistor from going into saturation. Okay, also extra current of M11, say during a negative step, is drawn from transistor MX, and that means there's more slewing current. This is M4 current also increases. Therefore, there's more slewing current. All right, so this is a nice technique, and in practice, if you run the numbers, if you do this for your project, for instance, you might find out that you perhaps have a 50-60% increase in your slewing current. That's significant, right? So you've cut your slewing time in half or maybe more. Yes?
But this is still considered to be a class A?
Yeah, well, it's pseudo class A, right? Because the current will still limit, right? But at least it grows. So if you look at the current available to slew as a function of input step size, it does grow, and then finally it limits. So you bring up a good point. What about class AB stages? So let's say, so in fact our next topic. So the idea behind the class AB stage is if I look at my output current versus the input differential, all of the problems that we've encountered are because the input current saturates, right? And what we just looked at was a technique that could increase this current if the input gets large enough, but it still would saturate eventually. Isn't it possible to design a circuit such that the input current is never, even if it's nonlinear, I don't care, as long as it just doesn't stop, as long as it doesn't saturate. So if I have an input stage that has a current voltage relationship like this, then I'm never going to slew, right? Slewing only happens when the current is fixed. If the current can increase in proportion with the input step size, then I have an exponential response, right? And so the question is, how do I generate a current like this? Well, resistors don't limit, right? So why not use resistors at the input? So here's one idea. What if I had some buffers at the input that applied my differential input voltage across a resistor, and then this resistor generated a current, and let's say somehow I now take this current and mirror it appropriately to my output stage. Okay? And presumably I can take advantage of both sides here. So I can somehow detect the current flowing through this resistor and then mirror it to the output. Okay? If I could build this circuit, certainly the slew rate performance would be very good. So let's look at a few implementations. Alright, so the basic building block, so for a BJT class AB input stage, is basically just a voltage follower on the basically N and P side. So I could take a differential voltage here. If these are good followers, the differential voltage appears here. And now if I can take the collector currents here and mirror them to the output, right? So let me build a more complete amplifier using this approach. It's going to look complicated at first, but then if you stare at it for a while, you'll see that it's exactly what we've described. So this is just a level shifting diode here. And that pretty much completes it. Well, let me draw a second stage here. Still need to get some voltage gain out of this guy. And let's say this is my compensation capacitor. So this op-amp topology is not so different from what you've seen before. You have an input stage, which is just a GM stage, and it basically is followed by, let's say, some voltage gain stages with some compensation capacitor across here. Okay? So the idea is that this amplifier will not slew limit because the available current generated by this buffer stage, this GM stage, let's say, is basically unlimited. If I keep increasing the input voltage, the current just keeps increasing. So how does the circuit work? Let's say I just ground this side and apply a large voltage here, right? So that large voltage now, this is just a follower. It appears across here, right? And that generates a current which basically flows into this node here. Likewise, the same large step generates a current here in this direction, which also sums with this current, and so we get the total current being a sum of this branch and this branch's input current, small signal input current. And the reason the circuit works at arbitrarily high voltage is you can see that even as practically, of course, I'm going to be limited by the supply voltage, because eventually these transistors will cease to be in the forward active region. But even if I apply a full supply voltage here, this follower is still happy. It's got current flowing in it. It will generate a voltage across here, which will generate a current. And so because the input never limits, even up to a supply voltage, this input stage never limits. And so the input-output characteristics, instead of being like that, with a diff pair, are actually going to be just a straight line, with the input, let's say, with the real limitation being VCC. Okay? And the basic building block is really just this circuit. I'm using this circuit twice in parallel. Okay? Now, why do I need these level shifting transistors? Well, you can just see that if I want to have the same DC voltage at the plus and minus input of my op-amp, then if I go down a VBE and then down another VBE, so that's 2 VBEs down, I need to go up 2 VBEs. So these stages here are just acting like level shifters. All right. So what are some of the advantages and, well, let's say disadvantages of this circuit, because we've talked about the advantage. Okay, let's get somebody new to answer this question. What's a potential disadvantage of this circuit? Anyone?
GM can change during the normal operations, and also output resistance is small.
Okay, we know how to fix output resistance, right? This is actually probably a real op-amp, so this is going to have a buffer stage. Okay, but how practical is it to build a circuit like this? To address your question, your point of the GM changing, actually you want the GM to change. That's the whole point of the circuit, right? So that you have lots of current for high input. But nominally for small signal inputs, the GM is fixed, right? The GM what's the GM of the input stage? Yeah, it's just 1 over R, right? And that's pretty constant. So, the GM is really the slope. In fact, I misspoke earlier. The GM does not change. The GM is roughly constant with input voltage. So what are some of the other issues, practical issues with building this circuit?
The area of the resistors? No? Because how large is this?
Actually, you probably are going to use small resistors, right, to get lots of GM. So your resistors are kilo ohms or less. Okay. Well, I'll give you one bad thing and let you guys think about the other. You need a PNP at the input, right? And PNPs are usually dogs, right? They're slow. They're very slow. So if you try to build this in a normal bipolar process, the speed of the input will be limited by your PNP followers, okay, which is bad, right? I mean, that's not supposed to be the dominant pole. This is supposed to be the dominant pole. So this will only work if you have what's referred to as a complementary process, a bipolar process where you have both vertical PNPs and vertical NPNs, in which case their speeds are comparable, let's say a factor of 2 or 3 worse, but still the bandwidth of a follower is not going to be your dominant pole. It's going to be basically fast enough. Right? Bandwidth of a follower is roughly ft. So you need the bandwidth of this device to be at least on the order of the non-dominant pole of the system, which is also usually on the order of ft. So maybe this will be the non-dominant pole. Okay, what's another problem with this amplifier? Well, this one's a little more subtle, and if you go through the analysis, you'll find out that, first of all, not only do we need fast PNP, but also there's a large systematic input offset. Okay. Let me show you one more class AB input stage. And essentially it's very similar. And so the idea is that instead of using one follower, I can use two followers. So this is my buffer stage. And then I would connect my resistor here, and then I would have one more of these buffers on the other side, right? This whole thing is the buffer. And then I could tap, let's say, this current and this current, feed these into a mirror, and go into a high impedance node. Okay. Now what's an advantage of this architecture, let's say, over this architecture? Any guesses?
Less offset.
Actually, no, this also has the same offset problem. Good guess. Well, when you design an op-amp, basically an ideal op-amp has infinite input impedance, right? What's the input impedance of this circuit? Well, it's basically emitter followers which are degenerated, right? So the impedance is going to be roughly 1 plus GM RE, which is really the GM of the circuit that you're going to get. So the input impedance, because this R is not too large, right, because you like to get good GM, the input impedance might not be sufficiently large, right? And so if you look at this is basically like a Darlington input stage. Its input impedance is very large, because now instead of seeing this R, you get an extra buffer in there. So you get like a beta squared times increase relative to R, rather than just a beta improvement in R. Okay? So this has a higher input impedance. And let me draw the full circuit so you can get a little bit of idea. These circuits take forever to draw. Okay, so here's one input. And let me just take this output and go through a current mirror. Actually, let me make it a high impedance current mirror. And again, I'll avoid redrawing this. It's the same thing. Okay, first of all, what's the gain of this circuit? So what's the open loop gain? So I apply a voltage here, I apply a voltage here, that gets applied here, right? So I get a differential current. And so this current is V differential input over R, right? If this current is positive, it's supplied by this guy. If it's negative, it's supplied by this guy. Then this current gets mirrored over here. Let's say I've built in a factor of M in my mirror, so I get an extra factor of gain here. And then this mirror flows into a high impedance load, right? So let's just call this Z1, which is the impedance of this Wilson current source, which is roughly beta squared RO, right? So the gain here is going to be, so this is the differential output voltage. So the output voltage is, the gain is Z1 over R times M. And then just plugging in some numbers, let's say this is beta squared RO, this is R, M. Let's say this is 10. Let's say this is just 100 to make the math simple. And let's say R over R is also 10. So I have 100 times 10 to the 4, or about 1,000,000, 10 to the 6. So I can get a respectable amount of gain out of this circuit. I mean,
Where did the beta squared come from?
that's the output impedance of this mirror, right? Order of
Beta over
magnitude.
2.
Yeah, beta squared over 2 RO.
Beta over 2 RO.
Actually, you're right. It's beta 2. Yeah. Wilson current source. Yeah, you're right. It's beta. Yeah. It's been a while since I worked with bipolar. Okay, so you only get about 10,000 gain out of this amplifier. So what's another advantage of this amplifier over this one here? They both have a class AB input stage, right? So they both have very fast slewing. But I'm using a different kind of buffer, and also I don't have the second stage here. So what's an advantage? What's a disadvantage, if you like? Anybody? Advantage, disadvantage? If this were an OTA, we could just take the output here. If this were not an OTA, I could just add another buffer to drive the output. In fact, the same buffer architecture I used at the input doubles nicely as an output buffer as well. So, what's the non-dominant pole of this guy?
The mirror pole of the Wilson?
Yeah, it's going to be either the mirror or potentially the input stage, depending on how fast these PNPs are. So the advantage of this architecture over this architecture is simplicity. Here we have potentially, we're doing pole splitting on this architecture, and we have kind of a competition between these non-dominant poles at the input and some of them here. Over here, it's very simple. There are very few poles in the circuit. There's one big pole here. The mirror is pretty fast, right? That's going to be on the order of FT. FT over M, if we have a factor of M here. And then you have also a factor of FT for the PNP stages. So probably your non-dominant pole is going to be FT over M, the PNP FT over M. Okay? And if you play around with this circuit, you'll notice that I can get more gain out of this if I also make use of these currents. So if I appropriately mirror the currents on this side, I can also add to the gain. So I get another factor of 2. Okay? All right. The next topic, which is an interesting one, is what are so-called current feedback amplifiers. And the idea is that, if we build an op amp and we do something like this, this is really a voltage feedback circuit, right? I apply my input here, I take my output voltage, I take a fraction of it, and I subtract it from the input voltage. And so the action of the feedback is to take the error signal, the differential input, and drive it to 0, right? And this is a general purpose op amp. Let's say you're designing. It has an output stage because it's driving a resistive load. And so if you're designing this circuit and you're a user of this op amp, what's likely? So what this op amp is properly compensated and everything, so you don't have to worry about it. Let's say it's compensated to be stable under unity gain condition, and certainly here we're using some feedback, so we have some gain, so it's going to be stable, right? But let's say we build this circuit and we find that it's ringing, it's not stable. What could be a potential problem here? Or let's say alternatively, instead of it ringing, we find that it's much slower than it's supposed to be. Looked at the data sheet, we put everything on the board, measured it, it's slow. Right? Well, clearly there's something going on with the parasitics, right? When we put this into a board environment, there's some parasitics. What parasitic in particular could hurt us? There's 3 nodes in this circuit, right? I could have parasitics here, here, or here. Where is it going to hurt? Anybody? Certainly it's not going to hurt here, right? This is a voltage source. Let's say I'm driving with a really small source impedance. Okay, so now it's a 50-50. Is this going to hurt us or is this going to hurt us? Okay, Tim. Use the mic.
The output?
Actually, no, because the output... Why do you think the output's going to hurt us? Can you use a mic?
Maybe due to the load at the output.
Well, remember, this is a op amp, right? It's not an OTA. So the output impedance is very low. So the extra pull you would get from this output impedance is going to be very small, right? Let's say the output impedance is an ohm, 10 ohms, right? It's not going to really affect us. So this output stage can easily drive this capacitance very high speeds. It's not going to be a problem. And remember, this is not going to affect the compensation because this op amp is internally compensated, right? So this is not adding to the compensation cap. Well, then there's only one choice left. This is it, right? So we have some capacitance at this node. It's due in part to the input capacitance of the op amp and also some parasitic capacitance. Because at this node, if I look into here, I see a high impedance. So the only impedance I see is looking back here. So the impedance I see is, let's say, R1 in parallel with R2, which is on the order of kiloohms. Okay? So you would say, just use smaller resistors, right? Why do I use resistors on the order of kiloohms? Why not use 10 ohms? Anybody? what determines the size of those resistors? Michael?
Yeah, I need to drive a current through the resistors for the other.
Yeah, I've got to drive current. So this op amp, as good as this output stage is, I don't want to load the output. I don't want to have to drive a 10 ohm load, right? So basically this size is set by drive current. And also, the size is also set in part by noise considerations, right? Because I know the feedback network does contribute noise. All right, so now let's say, what's a typical number here? This could easily be 3, 5, 10 picofarads, right? Let's say 3 to 5 picofarads. And so if I calculate a time constant here, I have 5 pico times 1 kilo ohms. And easily this could be on the order of, I don't know, 5, 10 milliseconds. You guys have a calculator. Let's see. So K times this. Yeah, it's on the order of milliseconds, let's say. Nanoseconds. Wait. Yeah, let me see. 10 to the minus 12. Yeah. What am I thinking? So, yeah, that's right. So this is on the order of nanoseconds. And so can someone divide the 2 pi and just tell me what the pole works out to? Somebody have a calculator? I have a calculation here that's 50 megahertz, but I just estimated it could be. But the point is that there are many applications where you're trying to design a circuit that runs at several hundred megahertz, right? And it needs to drive, it's in a board environment. And now, just because the parasitic capacitance this node, I get a pull that's much lower than I expected, right? And so all of a sudden, this high impedance node is hurting me. So what's the solution? What can I do to avoid this problem? Besides just burning more current, right? One option is just reduce these resistors. Anybody have a suggestion? I could do something really stupid, right? I could just put a resistor here. Small resistor, let's say a kilo ohm or something. Maybe in this high-speed application I don't care about my input impedance. Kilo ohm is fine. And then now gives me another factor of 2 roughly, right? If these are on the order of kilo ohm. So then I say, okay, factor of 2 is not enough. I need a factor of 10. So now I've made this 100 ohms. Now I'm loading this source down as well, right? Not to mention the extra current that flows through this resistor. So clearly that's not a good solution. So somebody came up with this idea of low impedance summing node. So what I'm going to do is I'm going to take that same op-amp input stage that I showed you, the kind of the Darlington-like class AB stage. And so here, remember I had a resistor, and then this was connected to another buffer. I'm going to get rid of that buffer and just call this the minus input. Okay. And then I'm going to go through a current mirror like before. And this is my compensation stage, and maybe I add an output stage if I need it. Say in this application I do. Okay, first of all, does this circuit even work, right? Isn't it kind of weird that I've eliminated this buffer? So usually when we think of an op-amp, we think it has very high input impedance. So now on this side, I have a high input impedance, but what's the input impedance on this side? It's small, right? Because it's R in series with 1 over GM. So you might be wondering, first off, does this idea even work? And then, you know, let's call this resistance R1. So first of all, let's see that this circuit has gain. Well, the operation of the circuit is not that different from what we discussed before, right? I have a positive input voltage here. This buffer just copies the voltage over here. I get a current, which is V plus minus V minus over R1. This current gets mirrored M times M differential R1. And then finally, this current ends up on this node, which has a high impedance, let's say Z high. So the open circuit voltage gain is very much like before. So the gain is basically Z high over R1. Okay? And if you plug in some numbers again, let's say this is beta over 2RO, this is R, and let's say we have a process where the transistors have high beta. Let's say it's a fast process. In fact, you get that for free if it's a fast process. So let's say I have a beta of 500, RO over R, and so then let's say we have 500 over 2. Let's say RO is 10 kilo ohms. This is 10 ohms. So this is 1,000 times 250. So 250,000. So the circuit has voltage gain. The problem is that it doesn't really, it seems kind of weird. It breaks our intuition. In fact, let me try to draw an equivalent circuit of this. So equivalent circuit. Remember, for an op-amp, the equivalent circuit is very simple. You have infinite input impedance, you have zero output impedance, and you have infinite gain. Right? But now my equivalent circuit looks something like this. I have a buffer, and now instead of gaining the voltage difference between these nodes, I gain the input current. So the input current is the current, let's say, flowing here. Let's call that IN. There's very little current coming here, right, because this is a high impedance node. But because this is the low impedance node, there's current flowing. And basically I take that current IN and multiply it by some large impedance Z, and that produces my output voltage. So this is a ideal op-amp, and this is the so-called current op-amp. Does this equivalent circuit make sense to everybody? Let me explain a little bit more why this current IN gets magnified. If I apply a positive input, right, the current supplied to the negative terminal comes from this transistor, right? So this would be my IN. And this current gets magnified once by the mirror and then magnified again when it flows into this output impedance. If I have a negative input voltage, then the current goes in that direction, and so again, IN is supplied by this transistor, which also gets mirrored and magnified to the output. Okay? So this is actually a pretty good equivalent circuit for this device. Okay? And of course, this is a voltage source, not a current source, because I have a buffer stage, right? So I take this high impedance node and convert it into a low impedance node. So let's actually show that, first of all, this circuit does work. So I'm going to take the same amplifier that you're familiar with in voltage mode and show you that it actually does work in current mode, although in a very different way. Say this is R1, this is R2. Alright, so what I'd like to know is In, and I simply observe that In is the input voltage, right? This input voltage gets copied over to here by the buffer stage. So the current In has to equal to V input over R1 plus V input minus V output divided by R2. So this is V input 1 over R1 plus 1 over R2 minus V output over R2. Yes, question?
Why in the negative terminal is also same potential VI? Because do we have internal resistance in the between?
Look at the equivalent circuit. The equivalent circuit is that this is just a buffer, right? Voltage buffer.
Okay.
So whatever voltage is here gets buffered here.
But if we look at the complete circuit, we have R1 in the between the V positive and V negative.
That's true. That's a good point. But this is usually a small resistance, right?
Okay. Okay, I see.
Yeah, yeah, you actually have a good point. And the point that you raise is going to turn out to be kind of a thorn on the side of this amplifier. But for now, let's neglect that. But yeah, good point. We'll come back to it. Okay, so here's the idea: is that this current, which ideally should be 0, right? For an op amp, what should be the input current? It should be 0, right? So really, we hope that the feedback is going to drive this current to 0. This is the error signal. So instead of having a voltage error signal, we have a current error signal. And then this is our feedback signal. So we take the output divided by R2 and we have a current. So it's really a current feedback signal. And this is why people like to call this a current feedback op amp, because the feedback is actually a current signal. All right. So now let me substitute that V out is Z times In. Right. This is the equivalent circuit. So the output voltage is just Z times In, and I substitute here that I have V out over Z plus V out over R2 is equal to V in divided by R1 in parallel with R2. And I can write this as V out divided by Z in parallel with R2. So that the transfer function V out over V in is Z in parallel with R2, R1 in parallel with R2. And if Z is very large, right, then it's approximately R2, R1, R2, R1 plus R2, or it's 1 plus R2 over R1. Just as you expected, right? So the external behavior of the circuit is very similar to a voltage feedback amplifier, but internally it's doing something completely different, right? And interestingly enough, the advantage that we get out of this amplifier, one of the advantages you see now, is that this summing terminal is low impedance. So any kind of parasitic capacitance here doesn't hurt us as much as it did in the voltage amplifier case. Okay. Questions? Alright, so this is actually kind of the ideal gain when the loop gain is infinite. Alright, so what is the loop gain of the circuit? So to find the loop gain, I'm going to break the loop at the output. Since the output is an ideal source, I don't have to worry about loading, and so this is my return signal. So I apply a test signal at this point, and then I observe the return signal. Well, because this is a buffer, the input voltage 0 here is going to be roughly 0 volts at this node as well. And so the current through the R1 is going to be about 0, so most of the current is going to just flow through R2. So I'm going to have Vx over R2 flowing, and therefore VR is going to be Z times In, which is Z times minus Vx over R2. So that the open loop gain, or excuse me, for the loop gain is minus return signal over Vx is simply Z over R2. And so as long as I choose R2 wisely so that R2 is much less than the internal Z, then my loop gain is going to be large. Okay. It's kind of funny, right? The loop gain, you have to make sure, you have to know that internal impedance. So when you're designing current feedback amplifiers, it's the internal impedance that's very important, and you know, if that really determines everything. All right, let me go back to this expression for the gain, and now I'm going to keep it. So I had that V out 1 over Z plus 1 over R2 is equal to V in divided by R1 in parallel with R2. And I just neglected this term, but let me keep that term. So this, I'll divide it by Z of 1 plus Z over R2 is equal to V in R1 in parallel with R2. And so now I'm going to write V out over V in is equal to Z R1 R2 R1 plus R2 1 plus T. Right, this is T, the loop gain. And this, of course, is also T. So I can write this as 1 plus R2 over R1 times T over 1 plus T. So this is the ideal gain, and this is the error, which goes to 0, which goes to 1, basically, for large loop gain. Okay. Now, what's somewhat surprising at first is that the gain bandwidth trade-off of this op-amp is very different than a voltage amplifier. Okay, so all we have to do is assume that Z has some dominant pole. Right, so at DC we have Z naught, but this is our compensation point, so this is the dominant pole. So now our loop gain, which is a function of frequency, is just Z over R2. And if I look at my gain expression, my closed loop gain is this ideal factor times T over 1 plus T, which I can write as 1 over 1 plus 1 over T. And if I substitute now, I have 1 plus R over Z. So this will give me R2 over Z naught, 1 plus J omega over omega naught. And I'm going to just drop this term R2 over Z naught. It's very small. And so I get 1 plus J omega omega naught R2 over Z naught. So this is my closed loop bandwidth, which is Z naught times omega naught divided by R2. So what's interesting about this expression? And I think back to your ideal op-amp, right? For an ideal op-amp, what's the bandwidth in terms of the open loop bandwidth? Anybody? Is there anything unusual about this? If you derive this on a test, you might think I made an algebra mistake, right? Let me go back and redo it. Why is that? Why should you be suspicious of this result? Yes.
The bandwidth here doesn't depend on the gain, it only depends on R2.
Yeah, very good. So this only depends on R2, whereas the gain is R2 over R1. So in effect, it looks like there's no gain bandwidth trade-off. I can just select R2 to get the desired bandwidth, and then any value of gain gives me basically the same bandwidth. Right? That's pretty nice. That's a nice feature of this op-amp. It means that the gain and bandwidth are decoupled. Does it mean I can design faster amplifiers, though? Ultimately, no, right? Ultimately, so if you had a comparison of voltage amplifier versus current amplifier, and all you're trying to do is get the most bandwidth possible, at the end of the day, you're going to get the same bandwidth for a fixed design. Let's say you design your circuit to have a fixed gain. Both cases will give you the same bandwidth. The nice thing about this is the flexibility, that it lets you trade off, change the gain without altering the bandwidth. But if you had done this for a voltage amplifier, you would not have that same flexibility. Okay? So, in terms of gain bandwidth product, it seems like this is potentially a win. Yeah, Shiji.
So in here, when R2 is increasing, when R2 become larger, then the pole becomes smaller, but in the DC gain also become larger. If we ignore one, then still have gain bandwidth product. If R1 be fixed.
So, yeah, so the idea is that these are decoupled, right? That's the whole point, is I can have gain even though I can alter the bandwidth without altering the gain, right? And vice versa. Let's say I fixed R2, say 10 ohms. And let's say I get a certain bandwidth. Now I can just change R2 and keep getting more and more gain, right? So, yeah, I'm sorry, changing R1. So the idea is that it seems like this could go on arbitrarily, right? I could just get more and more gain and still have the same bandwidth, right? The problem is what you pointed out earlier. The buffer has output impedance. So if you repeat the calculations with the buffer's output impedance, you'll find that something does give eventually. And so you don't get infinite gain bandwidth out of this amplifier.
Question?
Yes.
What I don't understand about the argument that you made is that in a normal amplifier we also have 1 plus t times the omega 0 is equal to omega 3 dB.
Mm-hmm.
So here you have t times omega 0. So you're always like dependent on the loop gain.
So in a regular amplifier, we can write an expression that the gain times the bandwidth is a constant, right? And so if I increase the gain, the bandwidth has to come down. Right? This equation doesn't apply for a current feedback amplifier. Okay. Yes.
Actually, if you do the math, the gain bandwidth product is going to be proportional to 1 over R1 actually.
So let's do the math. So the gain is 1 plus R2 over R1, right? Okay. And so this is approximately Z naught omega naught over R1. So I can make the gain bandwidth product as high as possible by making R1 small.
So basically there's a trade-off because we don't want R1 to be very small because of the power stuff. Is that
Well,
right?
forget that for a moment, right? In this gain bandwidth, there's no consideration of power. Yeah. But the reality is that this equation falls apart if you take into account the output resistance of the buffer. Yeah. But it does apply to a large extent. Okay. Now here's a question. Why not design this in CMOS? Right? Why not use this concept? Why have I shown it in bipolar? Why not build a CMOS version? What's that? Well, that's a good thing, right? Yeah. I mean, people have, for generations, made careers of taking old ideas and reinventing them, right? So you take vacuum tube amplifiers, you put in bipolars, publish a paper. So why not go out and just do this with CMOS and have a nice, fast slewing CMOS amplifier that also doesn't have a gain bandwidth trade-off?
Then in the BJT we using the input current and then.
No, remember it's the input current from the low impedance side, right? So even in the BJT version, the input current here is approximately 0, but there's input current here because of this transistor, right? If I did MOS, everything still works, right? There's no current here, but there can be current here, and I use this current to get gain, right? So what gives? Why not do this in CMOS form? Noise. I haven't thought about noise, but I have another better reason. Well, it's subtle. It actually goes back to what Shiji brought up. You need low output impedance here. So if I use MOS devices, their GMs are considerably lower, and so the impedance goes up, and that's actually pretty detrimental to the operation of the amplifier. Okay. Now, in terms of actually another question that Shiji asked, he was saying, why is it that R1 wasn't considered in the equivalent circuit? Well, the reason is that you at some point you realize I don't even need R1. R1 can be totally part of the feedback network. It doesn't need to be an explicit part of the circuit. Because the gain depends so much on R1 and I want to make R1 small, just get rid of it. Make it 0, right? The circuit still works. And as R1 goes to 0, that's the equivalent circuit that we drew. Right? This is the equivalent circuit with R1 equal to 0. And so now the gain of the amplifier depends on what you hook up to it on the outside, the open loop gain, which is slightly different from a voltage feedback amplifier, right? In a voltage feedback amplifier, the gain is just a bunch of GMROs, right? It has nothing to do with what you hook up on the outside. Here, it depends on what R1 value you choose, okay? And I think I called it R2 later or something, so guys can look at the notes and figure that out. All right, so get started on your projects.